You know what breaks most recursive solutions, especially in a coding interview? It's usually not the logic, it's getting the function to actually stop. So today, we're going to tackle the two biggest bugs that can completely crash your recursive code. And more importantly, we're going to learn how to write bulletproof solutions that really work. Let's kick things off with a piece of code that looks totally innocent, but is hiding a fatal flaw.
Okay, so take a look at this. On the surface, it seems super simple, right? We've got a function, countdown_bug. It takes a number, and then it just calls itself with that number plus 1. Simple. But if you actually run this, it doesn't just fail. It brings your entire program to a screeching halt. So what's going on? Why does this tiny little function cause such a massive catastrophic crash? The answer, it's a classic error, a stack overflow. It's like this silent killer that just builds up in the background, call after call after call until, bam, your program is just gone. But what even is the stack? And how in the world did we manage to overflow it?
To solve this mystery, we've got to look under the hood. There's this hidden piece of machinery that powers every single function call you make, and it's called the call stack. Understanding how this thing works is the absolute key to figuring out why our little function failed so spectacularly.
All right, first things first, let's get our definition straight. At its heart, recursion is just a function that calls itself. But for it to work right, it has to follow a really important pattern. Every time it calls itself, it has to be working on a smaller version of the problem, getting simpler and simpler until it finally hits a base case. And that base case is just a condition so simple it can give an answer without having to call itself ever again.
A really great way to visualize the call stack is to think of a stack of plates. Seriously, every time a function is called, you put a new plate on top of the stack. So, factorial of 3 gets called, we add a plate. It then calls factorial of 2, we add another plate on top. Then factorial of 2 calls factorial of 1, one more plate. When we finally hit that base case at factorial of 1, it just returns a value. And that's our signal to start taking plates off the stack, one by one, passing the results back down until we get our final answer.
Okay, so if we want to stop our stack of plates from crashing into the ceiling, we need to follow 2 rules. And these are non-negotiable. Think of them as the golden rules that separate beautiful, working recursive code from a ticking time bomb.
Rule number 1 is simple. You absolutely must have a base case. This is your function's stop sign. It's the condition that tells it, okay, we're done here, no more self-calls. But here's the kicker. It has to be a condition that your function can actually reach.
And rule number 2 goes hand in hand with the first. Every single time you make a recursive call, you have to be getting measurably closer to that base case. If your stop sign is at 0, your inputs better be counting down towards 0, not wandering off into infinity.
All right, with those 2 rules in our back pocket, let's play detective. We're going to go back to our original buggy code and pinpoint exactly which rules it broke and why it was just destined to fail from the very start.
And here it is. This is exactly where our code went off the rails. On the left, the buggy version calls itself with x plus 1. So if you start at 5, the next call is on 6, then 7, it's running away from the base case of 0. It completely violates rule number 2. The fix, on the right, is so simple it's almost beautiful. Just change that plus to a minus. Now with x minus 1, we're making clear measurable progress toward our base case, and the function stops perfectly.
But you know, there's another hidden danger lurking here. What if your code follows both rules perfectly, but the recursion is just way too deep? A classic example is the naive recursive function for Fibonacci numbers. It's technically correct, but it branches out so many times that its time complexity is exponential. For even a medium-sized number, it ends up making a mind-boggling number of calls, creating a very, very deep stack.
Now, if you've dealt with this problem before, you're probably thinking, aha, I know how to fix this, memoization. It's a fantastic optimization technique, and there's this common belief that it's the silver bullet for all recursive performance issues.
But, and this is a really critical misconception that's not quite right. Memoization is amazing, don't get me wrong. It drastically cuts down on time by caching results so you don't recalculate the same thing a million times. But, and this is the important part, it does not reduce the maximum depth of the call stack. The longest chain of calls from your starting number down to the base case is still there. And if that chain is too long, you will still get a stack overflow.
So, what do we do? If even correct code can fail, how do we actually protect ourselves? How do we write code that's not just correct, but truly robust and safe? Well, let's build our defensive toolkit.
The key here is to be proactive. So here are 4 defensive strategies. First, always validate your inputs. Don't let a negative number send your function on an infinite journey. Second, know the limits of your environment. Python, for example, gives up after about 1,000 recursive calls. Third, for simple long chains of tasks, just use a loop. It's almost always safer. And finally, here's a clever trick. You can pass a depth budget parameter that counts down with each call, acting as a safety net to stop the recursion before it crashes.
You know, this all leads us to that ultimate question every programmer faces. When should you choose the elegance of recursion versus the raw safety of a simple loop or iteration? It's all about understanding the trade-offs.
Let's just break down the Fibonacci problem with this side-by-side comparison. The naive recursive way is crazy slow and has a high stack risk. Memoization fixes the time, bringing it down to a nice linear O of n, but look, the stack risk is still high. Now look at the iterative solution. It's also O n time, but the stack depth risk? None. 0. For this problem, iteration is the clear winner when it comes to safety and robustness.
So what's the big takeaway from all of this? It's actually pretty simple. Use the right tool for the job structure. Recursion is a beautiful, elegant fit for problems that are naturally hierarchical, like navigating a file system or exploring a family tree. But for problems that are really just a long straight line of steps, a simple loop is almost always the safer and often more efficient choice.
So I'll leave you with this thought. Elegance versus safety. Both have their place, for sure. But understanding the hidden dangers of the call stack and always remembering Recursion's 2 golden rules, that's what gives you the power to make the right choice when the stack is on the line.